Progress a bit quicker. So I just want to go a little bit about manufacturing and then go to the system side. To market is really important how the prices developed in performance durability. And the energy storage I will make very short. So we talked about the solar cell, the photovoltaic effect. So we have here a voltage according to the internal electrical field, which is maximum 0.7 volts. This is for silicon technology. And if you want to have higher voltage, you have to interconnect those solar cells in series, so you can achieve higher voltages. This string, or if you put various strings together, it's called solar cell matrix. If you put it together, it's very fragile. So you encapsulate it in a solar module. So you put glass in front, plastic in between, make a frame out of it, so it could withstand 20 years or more. Usually the voltage achievable by a solar module is within 40 volts. Power nowadays 340 watts. So the biggest ones. Usually 60 cells, or since latest about 72 cells interconnected. If you want to have higher power output, you interconnect solar modules also in series. Why in series? Because the current stays the same, the voltage goes up. Nowadays, the maximum voltage is about 1000 volts, but there are plans to increase it to 1500 or even 2000 volts. And then you have to go parallel, and you have to go more to connect more than 20 or 30 modules. The rest you have to put into parallel. So this is the manufacturing. So you have here the solar cell, then the string, solder the strings, you solder the matrix, then do lamination, and then put the frame and timber, and then the testing to see what's the actual power output, because the cells, even a very good production, they are differing from each other in current, in power output. So these are cells interconnected in series. So that's the IV curve of one cell. It looks very small because the scale is very big. So this is about 0.7 volts. We saw this big scale before. Now it's very small here. This is one cell. Now you interconnect, for example, 35 cells. Then it looks like this one. You interconnect 36 cells in series. It looks like this one. So the current stays all the same. Only the voltage increases. This is the encapsulation then. So you have EVA, you have cell interconnectors, you have front glass and back foil laminate. Since nowadays the glass got very cheap, so they substitute the backsheet laminate, which has to be a very resistant foil, basically Kevlar from DuPont or other companies in order to withstand 20 years. Nowadays there's more tendency to put thin film glass on the back. Then you have the interconnector, you have the sealing, you have the frame, so on. Here there's a crosscut here to the cell, here the EVA, this transparent plastic to use there, it gets most as a copolymer plastic, and then the glass, and then the sealing, and then the frame here. So these are the cells. First, the cells get sorted according to their current. Why they are sorted according to the current? Yes, please. No, the current is. Oh, please.
Because if you put a cell that has a lower current, all solar cells have to put together in series. The current, the total current will be divided by the small current.
Exactly. So if you put all things current, the voltage doesn't matter. So voltage are all add up to high voltage, low voltage, it doesn't matter. But if there's one cell with a low current, it limits the current of all the cells. So you just put cells together, which in one module, which have the same current, and then make a module. And so you always see, if you have a brochure of a solar module, they have the same module but at different power levels, because this is due to the sorting of the current. So you find the module with 300 watt, 310 watt, 320 watt, 330 watt. The same module, same number of cells, but the sorting was different, and then you get different currents also from the module, also from the cell. The voltage and so on, all the same. And this is carried out here. So just manufacturer discussing whether they should make 11 classes or 10 classes, so they just sort according to a range of currents. This is here the interconnection here. You see here that they fix the wire here to interconnect the cells. It doesn't work always right, so here you see that depending on the quality of the manufacturing tools, also of the thickness of the solar cells, so there's a mechanical limit for the solar cells, so there was a tendency to make it really as thin as possible, but then there was a lot of breakage, so they make it now a little bit thicker than a couple of years ago in order to avoid such things. Then you have here the stripes here, the strings, and then you interconnect it here. This is a bit older one picture nowadays, it's more automatic, but nowadays you can't photograph it anymore in the factories, so these pictures are a bit older. I visit also some factories, but they don't allow any photos anymore, so I cannot show them, I don't have any of them anymore. This is in Indonesia, here also manufacturing, so they do it also quite manually, here, and then actually the distance, so it looks nice, so they're all the same distance here. And then you put the foil. This is the EVA foil. At the beginning it doesn't look very transparent, it looks semi-transparent, but as soon as you heat it up it gets totally transparent. It looks like glass then. The thing with EVA, you can melt it, and then it's fixed and you cannot remelt it. It's not a thermoplastic which you can melt and remelt. It's not possible anymore. If you once melted it, it has to be burnt to get it off. So this is a big problem with recycling. The other materials which could allow that, but they are much more expensive than the EVA. This is a laminator. So you suck out the air because you don't want any air bubbles. So you heat it up to 156 degrees, depending on the EVA and the additives. So they are cure, fast cure, ultra fast cure EVA. Depends on the cycle time and the cost you want to relate it to that. It takes between 7 and 20 minutes this lamination process. And then you put the frame on it. This is also nowadays automatic, so this is our old factory in Berlin. So they just it was manually, but not anymore. So here also the fixing here. Then you have the photo model to put in the terminal. This is also, you see here the according to standard test conditions, the power output here, monocrystalline and single crystalline cell. Multi-crystalline cell, thin film cell, this is amorphosilicon, so you have small stripes, so we have quite high voltages but a very low current, because the structure of the thin film module doesn't support currents more than 1 amp. It's also a combined carbon telluride, solar cell, thin film. We can also make flexible ones. Here you see one made in Brazil here. One flexible solar cell here. It's not only a cell, it's a system. So if you put it in the sun, it should start to glow. It's not too much. Let's see. So illumination. There's an LED connected to that. So it's not only a cell, it's a PV system with illumination. Sorry. There's a problem with the thin film. The efficiency is always a bit lower, and also lifetime is a bit an issue. Because nowadays, if you want to make large-scale systems, you have to have a bank which finances it, and they always calculate the risk. And if there's some risk involved, the interest rate is very high. And therefore, thin film power plants, photovoltaics don't play a role anymore because the risk is a bit too high. The prices went down a lot for crystalline solar cells, and so this dominate the market now. Just a comparison between different technology, basically crystalline and other thin film technologies. Usually you have a higher efficiency at crystalline silicon solar cell, so you need little area. Efficiency is lower for thin film technology, so you need larger area for the same power output. Usually they have higher temperature coefficients, so if you increase the temperature by 20 degrees, you have about a 10% loss for crystalline technologies. For thin film, depending on the technology, you have about half of it. Some of them have similar coefficients. It really depends on what you have. For the spectral efficiency, you have the highest efficiency at around 800 nanometers. That's the red part of the spectrum. For crystalline silicon, so it's better for large air masses. So if the sun is going down, crystalline solar cells have a little bit better efficiency. While, for example, amorphous silicon, it's more working in the central, it's more working in the blue part of the spectrum. The central part is carbon telluride and so on, for smaller AMs. So you have high price, not anymore, so it's a bit older, so it's substituted, but for sure long lifetime and warranties and good yield prediction also. The simulation programs, the structure doesn't change a lot. Whether you have thin films, they depend also on the history, what did the solar cell see, and then the chemical structure changes. This doesn't happen so much for the crystalline solar cell. So it's a real easy yield prediction, and it's good for long-term investments, and also good for low interest rates. While if you have lower prices for thin film, you can do more short-term investments. That's relevant for if you have high interest rates. These are some cost trends. This is here you see that the efficiency goes up for the different technologies. Here for different thin film technology. Here crystalline. So nowadays you can even get crystalline technology in the vicinity of 20% of efficiency. This is the prices here. Even when below that, so about 35 for thin film, crystalline is 36, so it's even a bit lower than that. Here you see the clear line. I come more a bit to the price a bit later. And if you talk about prices for the installed watt, we want to have kilowatt hours being produced, because that's the thing which is being paid, and not how much you installed. You want to have energy out of it. And this is not so easy. It depends on various effects. You have temperature effects, so with higher temperature, power output goes down. Also, at the standard test condition, you have perpendicular incidents. The truth is you almost never have perpendicular incidents, besides by tracking systems, but that's non-perpendicular, so you have higher reflections. So on, you should consider that. And also you have low irradiance levels. I was explaining you that about 2 hours ago, that you have low irradiance levels, that only the power output is going down, also the efficiency is decreased. And this depends very much on the solar cell materials and purity and so on. And as been also mentioning, there are spectral effects. Depending on the cell technology, it's more sensible in the blue or the red area. The aim is to get a good energy yield. So how much kilowatt hour of electric energy being produced during 1 year for 1 kilowatt of installed. This kilowatt installed, that's according to current standard test condition, is indicated by the small p. It stands for peak, and this means there's a nominal power output under standard test conditions. So it means 1000 watt per square meter, 25 degrees Celsius of operation temperature, and the spectrum equivalent to AM 1.5. So this is usually indicates that small p, because you see it often in brochures and so on. This was part of my PhD thesis, so just to calculate accurately the energy output, including here so you have direct light, it's easy to calculate because of the formula, but for diffuse light, how is the sky, what spectrum does he have, and from which directions come the light, and then I traced all the different rays through the modules and take a look at the cell reaching power here, the solar cell module, and then I check how much is converted of that into thermal energy and how much is converted into electrical energy with that model, and then you have data output and you find what is the actual power output. By the way, that's a nice thing for questions. What is the operation temperature of a solar cell with high efficiency? Is it lower or higher as a solar cell with low efficiency? We have two solar cells. One is a high efficiency solar cell, one is a lower. I put it in the same environment, the same irradiance, and I want to know which one develops the higher temperature. Megawatt? Oh, so let's make a quotation. Who's for the high efficiency solar cell? This is getting hotter. The low efficiency solar cell? Okay, that's right. Because what happens if you have the low efficiency solar cell, then a higher proportion is converted into heat, low portion is converted to electricity, and this heats up the solar cell. While you have a high efficient solar cell, ideally would be 100%, then it doesn't heat up at all, so it stays totally cool. Then everything is converted to the electricity, and you take away the electricity. Very good, not everyone knows it. This is just a model we made here, just how to really calculate that. I go quickly over that, so it's not so. This is also a model to see what's the cell reaching energy during the daytime. So this is a transmission of the encapsulation during the time of the day. Morning is not so good because you have a lot of reflections. This depends on what part of the model, how detailed your model is, whether you incorporate dispersion, that means the changing of the refractive index with the wavelength, then whether how many interfaces you are considering, and whether you take real incidence or perpendicular incidence, and or whether you consider the internal reflection, because some of the internal reflected part is still usable. But this is a different models here you have, and the black one is in all models included, so this should give the real optical performance of encapsulation. You see here that what I was mentioning 2 hours ago, the weak light effect. So you see here two modules, module A and module B. They exactly have the same power output at 1000 watt per square meter, but module B has an impure material. So you have better, not as good a weak light effect, so the efficiency is going down for low irradiance level, for example here at 300 watt per square meter. And that means that the energy yield is going down. The energy yield depends on the composition of the probabilities of irradiance values. So here, for example, Brasilia, you have a lot of irradiance which occurs at high irradiance levels. So here the difference is not perceivable, so you don't see a lot of difference. But for Frankfurt, for example, a lot of irradiance during the year occurs. Here 50% of the irradiance during a year is at that 300 watt per square meter, and here you see the differences. And here you see also the differences, module A and module B. In Brasilia, they have the same power output. In Frankfurt, they have different energy output during the year. Another effect. So we have series connection now, and so what happens if we shadow one cell? For example, they're shadowing. As we learned in the beginning, they could be shadowing from other cells, but for other buildings and so on. We take a look at. What happens, for example, if we have a cell that's shadowed by 75%? First, you have this curve here. It's shadowed by 75%, so that means you have only 25% of the original current here. But here this was more than 4 amps, so this has been more than 1 amp. So this and these don't fit together. What happens? This cell limits the current. It almost acts like breaking up the circuit. Here, you can show it here. So here you have 3 cells in the connecting series. Now we shadow the cell by 75%, and this limits the current. So originally this was producing something plus minus, plus minus, plus minus. It is in the connecting series connection. And now this is broken here. You can imagine this is broken. Forget this bypass diode at the moment. We'll come to this later. So it's open here. And then you have minus here and plus here. So this is the dominating voltage here. And this means that you have, compared to the original voltage, a reverse voltage here at this cell, which has the current limitation. And therefore, we have to consider the reverse current here. So there is a reverse voltage here And in order to find a common IV curve, we have to add these curves here, the 35 cells plus a shadowed cell, and this we do by superposition. So we take one sample point here at same current because it's interconnected in series, and then we add it together, and when we arrive this point. And this we do with all other points, and finally we have this curve here. That's our final curve with 35 perfectly functioning solar cells and 1 shadow solar cells. You see here, power output is very much lower than just if you could imagine that only 36th of the solar reduced, but it's here the total power production is much less than that. And therefore, it's a thing to avoid if the cell is shadowed. Also, you have high negative voltages here. Maybe you can even destroy the cell. And what you do against it, you saw it already, it's a bypass diode. So you put in a diode here, and this diode, normal condition, it's without shadowing. Just imagine this is a way, not shadowing. So we have here a cell plus minus, plus minus, plus minus here. So this is plus, here minus. This is in blocking condition. This diode, nothing happens. But if we have the shadowing condition, then we have a reverse voltages from that cell and from that cell the minus. Then the current starts to go through the bypass diode, and sure, you don't have any power output by this cell anymore, plus the voltage losses over the solar cells, but the total current is not limited anymore. And so you avoid a lot of losses, and this is implemented in the, so this implemented bypass diode you put here in the terminal box to avoid this. So every normal solar module has some of these bypass diodes. Ideally, it would be that every single solar cell has a bypass diode, but this became too expensive, so they put it to 1 or 2 strings together, which have a bypass diode. So you use the power of not only 1 cell, you use of 12 cells, for example, but it's still much less than you use the power of the whole generator. Another this idea of a German company who wants to make it electronically without any bypass diode, but finally it was too expensive and they stopped doing that. Now we come to the last part of the PV module. So we talked about the cells, the module, and the bypass diode. Now we come to the connection. Usually it was done by screwing, that you put in the cables. When I started photovoltaic, it was quite common. Nowadays the voltage really got high and up to 1000 volts, and also the necessity for fast installation came up. So we wanted just a plug-and-play solution. Then these plugs came up by a Swiss company called Multi-Contact. They just had these connectors, MC3. Then they came up with this one, MC4, which to snap in. So it's very easy to install, quite hard to de-install, because you have to press those at the same time. It's a bit hard to do, but while it lasts for 20 years, it's not so important, and usually they're quite reliable. So they're very quickly to install. Within a couple of seconds, you have the interconnection of those. They're totally water resistant, and also you can not tear the part anymore. So to avoid vandalism or something like this. If someone takes off here, this was still possible here, they don't take off the plugs. Okay, so at the end, this is just the conversion efficiencies. Just an overview. Just this is some laboratory. So 25% is a laboratory. If you go to commercial things, in the vicinity of 20%. Thin films also kept up very much. So this is quantum telluride. Our module is now even in the same range as crystalline silicon solar cells. So just also a play of efficiency and cost. So sure, you can make high efficiency solar cells, but at the end they get very expensive. So the highest efficiency solar cells, they are applied in space, because the costs don't matter so much there. So the space and the transportation costs are most expensive. And for terrestrial application, it depends really on your land costs and so on. How much is importation cost? This is important in Brazil because you pay 40% of import cost. So sometimes you have to think about this, and then there's simulations program for this, which find the best modules for you. There are big data banks with all kinds of modules, and then you can put in the different cost factors as installation costs, labor costs, cable costs, lens costs, and so on. At the end, you have the optimal solution. So not always the best, the highest efficiency is the best solution. Some configuration, so sure, if you put it in series and you can put only a limited amount of solar modules in series up to the voltage of 1000 volts. Also, you want to avoid if you have here a shadowing and you have a bypass diode working in and bypassing that part, then the voltage of one string would be lower than the other strings, which you put in parallel. Theoretically, that would lead to a case that the power of one module is not only going to the breaker or to the inverter, it's going to the other string of modules. It's not feeding the consumption, it's feeding the other modules. In order to avoid that, you put a kind of valve here. This valve is called string diode. This permits that the power is only going out of the module string and not inside the module string. This is quite common for large-scale installations. Disadvantage is that you have this string diodes in series, and they always are connected, so the current is going to them. There are some losses related to this, some voltage losses. Nowadays, they use type of fuses in order to avoid that the current goes in. It depends on the company you contract for installation. Some use string diodes and some use fuses in order to avoid that issue. Okay, this is about installation. I quickly jump over it. You can download it, so some recommendations about the installation, but while we have limited time, it's not so, can't go into details about it. So it's just important perhaps just to mention, you cannot switch off the modules. As soon as there's a slight, one photon is enough, then there is voltage here. So you're always working with, not like an conventional electrical installation where you switch off everything and then you install and you switch on. It's not possible with photovoltaic module, there's no switch here. You have the modules and they are always, during daytime or even at moonlight, they are producing voltage at least. Current is not so big at moonlight, but the voltage is already there. Therefore, you have to take care. You have these plugs now, and should remind that the level of current sure is proportional to the radiance, so that's clear. The PV arrays are current sources whose short circuit current is only about 20% more than the nominal current. This is different for a normal household installation, so you have the maximum permitted current of 10 amps and you put in a 16 amp fuse. This is not necessary for photovoltaics because the maximum current is only 20% more than the nominal current. So you put in a lower rated fuse and so on. Combiner, so you have just to, if you connect it to the main cable, you have to have an extra switch in order to avoid that you even work at the inverter with high voltages. This is just some other recommendations. I go quickly over that. Installation should be carried by, yes, dry weather conditions. Sure, if it's raining and the voltage is not so healthy here. Yes, this is also the installation. So this is just more for installers. If you want to get an installer here, you have all this. You have the PDF and can read it carefully, and then you already have the whole information on that. But while we have quite limited time, I go quickly over that. The earthing. So this is just some pictures here of that. So this is a DC connection box in China. This is a 127 kilowatt system. So they have here. Here should be the string diodes, but by the Chinese they want to save the costs of the string diodes. They put fuses here, and then they have plus 700 volts, minus 700 volts from the array. That means you have, I think, 21 modules connected in series, and then you have in parallel also 50 modules or so. And then they all connected here via the string diodes or the fuses, and then you have the DC switch, and this goes then to the inverter. It's a very typical configuration like this one. So you find it possibly here also in the 500 kilowatt system. This is calculations, how you calculate the losses of the cables. So you have the resistance of the cable, which depends on the length and the diameter of the cable, and then you have the specific conductivity. If you have copper, it is 56 meters per ohm millimeter square. If you have aluminium, it's lower the conductivity at 34 meters per ohm square millimeter. So you can calculate the resistance, and then you have here the losses. What you perhaps, for example, that's very common, you permit a 3% loss in the cable, and then you calculate the necessary diameter to do that. Okay, that's enough. This is what's for cables. These are also carried out usually in simulation programs, so you don't have to care about this. It's just for stressing the students a bit, so they have to do some homework and they can calculate something. But it's good to have an oversight of what diameter you should have. Inverters. So usually you have now a DC power output up to, depending on the size of your system, so the biggest one are up to 1 gigawatt. Moment, what are you doing with that power? You can have DC consumers like this LED, for example. This directly uses DC current, or you can connect it to a storage with a battery. It needs also DC, or you can feed it to the grid, which is the most common one. The grid is usually AC, so you have to convert it to AC current, which is synchronized to the grid. There are two kinds of inverters. One is autonomous inverter, which creates its own oscillator, which creates its own 60 hertz wave. The other one is just actually amplifying the grid, so you have the sinoid given by the grid, and it just feeds on the grid. I will talk a little bit on those ones principally, because these are the most often used, that the photovoltaic system is connected to the grid. So this is the key functions, as I mentioned already. So this converts DC to AC from the PV panels. This is maximize the harvest. There's usually a so-called maximum power point tracker related to that. That means it adjusts the load resistance in such a way that the current and the voltage is exactly at the maximum power point. So you get the maximum power out of it. If the irradiance goes down, you have to increase that resistance. If it goes up, you have to decrease that one. This is usually done by so-called DC-DC converter. Then oh sorry, you can't for me to read here. Can I take the microphone here? Yes, very good. So it manages grid stabilization through monitoring communication. So this is getting more and more common now in Germany. First, 10 years ago, it was just seen as an addition to the grid and something not really useful for the grid, so the utilities didn't like it a lot. Nowadays, they see advantage of it, and they use it really for grid stabilization. So they say before, for example, fault riding through. It means if there's a fault in the grid, 10 years ago, all photovoltaic power plants has to immediately switch off. So if the grid is not present, it has to be switched off. Nowadays they make the requirement, they say, no, it may help even if there's more blackout, then the photovoltaic power plants can continue working and overcome such problems. Also, with reactive power, there's a shift between voltage and current, and usually the utilities, they have special power plants which compensate that. But this can be also carried out by the inverters from large power plants. And this is now very common, so they send a message to the inverter, for example, of a huge photovoltaic power plant to put the shift between voltage and current to zero when it's been distorted before, and so on. So this is more, it has been possible also a decade ago, but the utilities ignored it a little bit, and nowadays they see also the advantages of those possibilities. Come to this a little bit later. Problem is still there's a country-specific grid and safety codes, so we've been visiting with some students this SMA manufacturer in Kassel, which is very close to Paderborn, and there we saw that for Italy they're a different inverter, or at least what they do now, they change the software. So this fault riding through and so on, so you can even change it later. sometimes the frequency requirements. Before in Germany it was that you have to immediately switch off when the frequency is going above 50.2 Hertz. Now they found out it's not very helpful for the grid because there are now 40 gigawatts of photovoltaics installed in the German grid, and if they immediately switch off, they have huge problems. And now they soften this, so some of the inverters they switch off at 50.1 Hertz, 50.4 Hertz, 50.6 Hertz to soften it when there is overproduction. And so on. So this is country specific and also changing with time. So this is a basic configuration here. So you have the PV modules. So you can have one module with a so-called module inverter or up to 25 modules, depending to the maximum system voltage. For example, 1000 watts. Then you have this maximum power point trigger, which is basically a controlled DC-DC converter. Then you have the inverter from 1000 volts input. Then you put it, for example, here to a single phase, but also triple phase, with either 230 volts or 400 volts, and inject it to the grid. For large-scale applications, you have going to mid voltages. In Brazil, I think it's 30.6 kilovolt. In Germany, that's 20 kilovolts. Or to the high voltage grid, which starts in Germany at 110 kilovolts. Medium high voltage is 220 kilovolts and goes up to 380 kilovolts. Only the biggest power plants do that. So this one in China, it was about 500 half a gigawatt power plant. They were directly, as you see the pictures later, they were directly connected to the high voltage grid. This is a basic layout of an inverter, a single phase inverter. What's now state of the art, or what's the so-called pulse width modulation. So you just switch on and off, and the switches, and the duration of the switching on and off after smoothing it by that circuit is then the desired output of your sine wave. So this is your desired sine wave. Here it's always switched on. So it means that it's just you cannot switch off a lot because you want to keep it at the nominal voltage. Here, for example, it's only half a voltage, so you switch on and off for half of the time. And if you smooth that out, then you will have a voltage which is exactly here on the half. Here 0, and then you have activate the other two. So here it's first your plus and here minus. So you just switch that off and switch that on. So you have minus here, and then you put this to plus, you switch that on and that off. So you have inverted pulse here, starting with a very small pulse in order to get this voltage, and so on. It starts here, almost permanently switched on for that voltage, and so on. So this is pulse width modulation. So nowadays all inverters or modern inverters do that. And then you go to the 8, depending whether you have 60 Hertz or 50 Hertz grid, do it here. This is for a three-phase system. So you have here for each phase you have 2 switches here. And the thyristors or MOS-FET, whatever. The MOS-FETs only is going up to 50 kilowatt. If you go higher outputs, you go to thyristor or other semiconductors. In order to save space and material, nowadays you have not only one large transformer which transforms that one to the desired voltage. You do DC-AC conversion here at a very high frequency. The advantage of that high frequency, you don't need a large transformer. It can be very small because the switching is very fast, and then it can reduce its size, and you don't need a lot of big core. You can use the weight of that. And then later you convert it back into 60 Hertz according to the grid line. So this is also state of the art. So this is just how you call this? There's a high frequency step in between. If you have a modern power supply of your computer, they all have this technology. Remember 20 years ago when you have a power supply for the computer or for charging a phone, it was quite heavy. Because there's a lot of metal involved, because you have the transformer, which makes a lot. Nowadays you don't have any transformer anymore. You have just a micro transformer like this one. If you're running at 100 kilohertz or 1 megahertz, it can be quite small. This is an efficiency curve, a very bad efficiency curve here. Usually people started in electronics, they just thought, okay, what's efficiency at 100 100% of the power output. And while very often this is not relevant, because often the power plant is not operating at full power because the sky is not clear and so on, and then you have reduced power output and also reduced conversion efficiency of the inverters. So theoretically, your ideal inverter should always provide constant conversion efficiency. Here you see the statistics here from Germany here, but this is Berlin. Perhaps you see here, these are hourly values. So you see here that most of the irradiance hourly comes at 400 watt per square meter. If you take minute values, because sometimes there is clear sky for a minute, it looks a bit better. So you have some minutes which have a quite high irradiance, quite high power output in irradiance, and you have to think about what's the average conversion efficiency, and this is done by so-called here European efficiency. It's not only applied in Europe, it's applied in many other countries also. So you do kind of weighting of the efficiencies achieved by the inverter. So you take first the nominal efficiency at 100% of the power output, but only with a weight of 0.2. Then the most important weight, with a weight of 0.48, is at 50% of the power output of the inverter. And then for 30%, it's with a weight of 0.1, and so on. So this gives a more an average or more weighted efficiency that is more realistic for the operation of your inverter. You see it here. For example, here you have the efficiency curve here. So here 95% of efficiency. This counts for 20% or 0.1. Then you have here efficiency of 95.4. This accounts for 48. And so on, and this is here, efficiency gets really poor here, but this doesn't count a lot here. You understand it? Okay. For example, here you have inverter 1, looks quite good on the data sheet. If you just see the 100% power output, you prefer to buy 1. But inverter 2, for example, has a lower maximum, but it offers better conversion efficiency over a whole range, broad range. Sometimes then is inverter 2 maybe better than 1. This is something interesting in order to, while you know that seldomly you reach the standard test conditions, that means 1000 watt per square meter and so on, you may even downsize the inverter. So for example, for a 1 megawatt system, you perhaps won't need a 1 megawatt inverter, depending on the location and so on. But for here, for example, for Germany, you see what will happen. So we say, okay, we save money, we don't buy a 1 megawatt inverter, it would be here 1 by 1. 1 megawatt for photovoltaics and 1 megawatt inverter. What if we buy only a 600 kilowatt inverter for 1 megawatt system? So we would still have 90.1% of the energy yield of that. So you don't lose a lot, even if you have half of the power output, because most often the power plant is not running at full power. Or here, for example, here 800 kilowatts, you only lose about 0.7%. You save 20% of the costs of the inverter, and this makes perfectly sense. Another things about inverters, this is a concept so-called master-slave concept. So for low irradiance levels, you have just one master inverter being switched on. If the irradiance is increasing, you ask some slaves to help you here, and then you arrive at a higher average conversion efficiency. So here would be with the one inverter only, so you have poor efficiency at low irradiance levels. Here is quite good. If you divide that into 3 inverters, 1, 2, 3, so for low irradiance levels you would only use 1 inverter, and then when it's not sufficient you call the second inverter, the second one slave here, and the second slave here. All together you see this blue line is average above the orange line. Means in average you have a higher conversion efficiency. This is called the master-slave concept. This is a configuration. As you know, just you have here modules in series and the DC switch, and then you put it to the grids. So this is a scheme for it. Same for three-phase system. So it looks the same as a string of modules, and then connected with a separate rod to each phase of the grid. If you have this configuration, you should always think about that you balance the phases a little bit. So you put this configuration to the grid and the other one in order to, if you have shadows or something like this, to give always the same load or the same injection in average to each phase of the three-phase system. Interesting concept is here. Sometimes you have uneven roofs, or you have a whole roof which looks in different direction. For example, one part of the roof is looking towards east, one is looking south, and one is looking west. Or in Brazil it would be north, not south. Usually it's quite bad to all connect them series because the lowest current determines the total power output. In order to avoid that, you can have a separate maximum power point tracker at each sub-generator here and work with full power of each of those sub-generators, and then only put them together at a common voltage and then put it to the inverter. One central inverter here, but before that you always control them via MPP tracker and put them via this DC-DC converter to the same voltage and then convert them. One step further is the so-called module inverter concept. You have an inverter at each single module, and then you interconnect all the generator only on the AC side. So here you have a maximum power point tracker and an inverter, and so each of those units is totally independent of the others. You can switch off one, you can additionally install another one, it doesn't matter. While you have one big generator central system, it's much more sensible to the changes of configuration. This is quite robust, so even if there is a shadow in one module, it doesn't affect the others at all, because these are these are really independent power plants here, consisting of one module and one inverter. So this we test a lot, so we compare different brands here and try to find out which is the best and which is the which gives the highest energy yield. Some publications, you find it on our website. You can see the results, what we found out here. Some advantages of the microinverters. Yes, you can have shading is much more tolerant against shading, and you can also monitoring of each single modules, because usually the inverters, they have a monitoring unit and they can transmit the actual performance of that unit. It's either one module or a string of modules. Yes, you can also have different modules because they all operate at different maximum power points, and this doesn't matter. Yeah. Additional advantages, logistical spare parts. So you only have one kind of inverter for different power outputs. Usually you should have, if you have different system sizes, you have 5 kilowatt inverter, 10 kilowatt inverter, 20 kilowatt inverter. But if you have microinverters, you can have hundreds of microinverters, and according to the system size, you combine them. Also effective mass production, so you can also produce more. There's also this advantage that the PID effect, potential induced degradation, is not occurring while the voltage is much lower. Also, while you can install the modules in different orientations, even non-optimal locations, for example, looking just towards sunset or towards sunrise, then you have a more equalized power output of the of your PV systems, rather than if all modules are looking in the same direction and then have the same the maximum power output all at the same time. These are power optimizers, what we have been seeing before. So this was the concept where you have here. This is a power optimizer. So these are units which are a bit cheaper than microinverter, and they are connected to each module. and then you have the optimal power output of each single module, and then you still need a central inverter. Okay, that was the inverter side. So we come now for the system layout for grid connection. So this is it's been many, so 1.5 million systems like this are installed in Germany. So you have a roof generator here, then you have the connection box, as you see before, for a large-scale system, but it exists also for small-scale systems, where you put them all together, and then you go the output here, which goes to the inverter, and then from the inverter you go via meter to the grid. You check to the grid. Formerly, about 10-15 years ago, you got a very high compensation, a premium tariff for your photovoltaic modules, for your photovoltaic energy generation, which was in the vicinity of 50 euro cents per kilowatt hour. This went down a lot because the cells got much cheaper. So nowadays you only get about, for private households, about 10 cents per kilowatt hour. For large scale ones, even below that, only 6 cents per kilowatt hour. Nowadays it's more attractive, while you're now paying about 30 cents for consumption of photovoltaic energy. And not consumption of energy from the grid costs about 30 cents. It makes much more sense to consume your photovoltaic generated energy directly. This is the DC box here, what you saw before. So the generator, the junction box was saw starting model here, and then the DC main switch, the inverter, and the cables and fuses to it. So this is a system configuration for a system which is larger than 30 kilowatts. So you have a, you should have a large central coupling switch, which can be switched on and off by the utility for large systems larger than 30 kilowatts. For really large scale systems, you can even, here for example, mid voltage or even high voltage, 110 kilovolts, I can even require some dynamic grid support. That means reactive power feed, fault right through, and so on, according to the requirements of the utility. Also, you can have controllers which provide static grid support. Means you have, for example, long lines, and you have a constant reactive power, so you know exactly what the compensation has to be in order to get it to a cosinus phi of 1. That means you don't have any phase shift between voltage and current. It could be constant. And also, network security management. So this depends on, because we now have 40 gigawatts of photovoltaics in Germany. So that means for some days on a weekend, when there's not a high industry consumption, photovoltaic can be the largest power producer for the German grid system. Sometimes there could be an overload, and so they have the right to switch it off in order to avoid a grid collapse. Usually you get paid also, even if it's paid off, the meter is still is calculating how much energy would have been generated if you feed that to the grid, and you get it compensated also. So there's no loss for you as an investor. That's very important. But in general, it makes the electricity much more expensive at the end, because the utilities pay for energy not being really used. This is an example of a mid-voltage grid connection. Here, mid-size transformer, and this feeds into the 20 kilovolt system. This is a large-scale mentioned in China, so this is 110 kilovolts. It is feeding directly here. This is all covered with photovoltaic cells, 500 megawatts here, just around it, just as you the main panorama picture to see that. These are the requirements. I don't go into details here. You can read it here later to see what you have to do. Depending on the size of the system, there are different safety measures. Very important also to see, to do maintenance and to see the performance. This is monitoring. So most of the modern inverters, they already have a monitoring system implemented already. So you don't have to buy it extra. Only for large scale, sometimes they have some provisions extra, and they even put alarm on your cell phone if the system is not performing very well. In order to check performance, sure, you have to measure the power output, but also you should be aware about the power input. So you should have a pyranometer on the incoming side to know whether your system is underperforming or sometimes overperforming. You want to know that. So we come now to second part of PV systems, mounting and BOS, balance of systems, costs of non-grid systems, and the costs. Mounting. So usually if you go to academic lectures, or people just like to talk about solar cells, about photovoltaic effects and electrons and blah blah blah. This is not really main issue. If you see what the costs are, things. So this is just usually what you do in such a lecture, talk about solar cell technology, diffusion and metalling and so on. But you have material costs, also module costs, glass frame, it's even more than the solar cell technology, and installation support, which is the highest part. The 35% of the total costs are in this vicinity. Nobody talks, there's no academic, there's not even a book about that. So just it's very purely, while there's a lot of conferences here about that part here, which is already squeezed out to the end. And here you can really get a lot out of it. So here, just to see what are the parameters which are relevant to the, for example, for the installation. So you have the grid load, you have the compatibility with the PV modules, then you have the materials, whether steel, aluminium, or wood. Wood is not really outdated. Sometimes wood is quite good. If you have maritime climate and there's a lot of salt in the air, it's more resistant than metals, because metals, if they're salty air, they get this maritime air is very aggressive. So sometimes wood is a quite good option for that, especially in dry climates. And maintenance, so you should also think about corrosion resistance, and sometimes the ground is not even, so you should be able to adjust it to make a nice even surface, because it doesn't look nice then, or it can cause shadowing and so on. The fixation of the model, the arrangement, you should always have planned before in order to really do it quickly. I'll show you later why. So there are some companies, specialized companies, who provide tools for that, so already pre-prepared tools. So this works quite quickly, so you just have to here put in the bars here for where you fix the models, and then this you can adjust in direction and in height also. Here also for the bars here, where you can also adjust the tilt angle and so on. To fix the models on the bar here, it's just about foundation here. This is a foundation, how it's been done in '94. So it's just people build a big concrete block. It took a month to build it, and then you put the modules on it, like this one. So photovoltaic was really expensive, so it made sense. Nowadays it's unaffordable to do it like that. So one step is just to make some kind of ballast here, just to fill some gradients here with rocks and so on, and then you can install it much quicker. So or you have prefabricated blocks that you just put in the ground and fix that. Or you can hammer in some tiles here. That's very often done, and then you don't need any foundation and so on, and it's quite cheap and fast. It can even be more faster than that. That's with the screws here. So you have just like you put a screw in the wall. You have some ground screws and fix it by that. For substructures on the roof, you can also have some modification in order to avoid a wind load here. Just we have a sheet here that directs away the wind, and so the wind load is reduced by that measure, and so you have to have less ballast on the roof, which is sometimes critical. Also some kind of to that very simple, but there are also some tools for conventional roofs here, some roof bars which can be adjustable. and so on. Usually you should avoid that that the water can penetrate through the roof, so you just put the tile here and then install the bar here, so there's no chance for the water to come in. A lot of tools here. This is for thin film modules. The thin film modules are frameless modules which are fixed by such module clamps, so they don't require any framing anymore. So this is just the module clamp here, just you have the module here and then you have the clamp, and then you have one single screw and you can fix two modules at the same time here. This is some examples here. Fixed modules. This is a tracking module which is not often used anymore because usually it's getting cheaper in the long term. This is also a tracking system installed in the east of Germany. This was after a big storm, so this was automatically directed in horizontal position to avoid the drag forces from the storm. Here you see the azimuthal tracking, and here the elevation angle tracking or the tilt angle tracking here. So costs of the PV power plant, so you have divided the costs, so these are the modules, so the parameters, you have efficiency and technologies, module properties, the lifetime and so on, warranties, and the local conditions. So this is array orientation, shading, snow and wind loads, soiling, to the desert and so on, so there's a lot of dust, so you should clean more, and grid connection, how far is it to the grid, what voltage does the grid have, and the site layout. Is it even, or you have some mounted, so on. Here are so-called balance of systems costs. So you have here, so also calculated same as a module as €1 per 1 peak. So it includes a substructure, foundation, inverter, monitoring, wire connection, and engineering, procurement, and construction called EPC. There are special also called EPC companies which do that. The margin and receptioners. So this divides into mechanical balance of system costs, so the mechanical part and the electrical ones. So see here the division, for example, here the ground-mounted systems, so not on the roof, on the ground. Here you see some different system configuration. So you have the PV module costs here. This is about the high efficiency module, so it possibly make about 60%. If you have, for example, a thin film modules, the modules cost much less as a share, but you have to spend more in the balance of system costs. Here you see more in detail what's the division of. So you have here substructure, the cabling, the inverter, cost for the EPC, mechanical installation, electrical installation, and so on. So here you have ground-mounted systems. Here you have a pitched roof, so the division is different. So here you pay less for the here the substructure is less relevant. Here you pay much more for the substructure, but for the roof you don't have to have a big substructure. For a pitched roof, especially if you have a flat roof, you have to consider a lot of substructure to put it to the right angle and so on, and to do fixation on the flat roof. Usually not allowed to penetrate the flat roof, otherwise you have the water can come in there. There's a lot of discussion sometimes that the energy required for building a PV power plant is very high and it doesn't compensate over the years. This has been a discussion 20 years ago, but still you find it sometimes if you go on Facebook, or sometimes some people really think that it's all completely nonsense photovoltaics because the energy being consumed from production is much more than ever comes out. This shows that they are also completely wrong. So this is the energy payback time, EBTP. So how many years you have to put the system into the sun until the energy being needed to produce that systems is back. And as you see here, even for the worst case here, monocrystalline silicon and 2011, so this is smaller system, it's less than 2 years for Brazilian conditions. If you go to a more modern system here, or to thin film, it's even less, so it's in the vicinity of 1 year here. Multi-crystalline silicon is in the vicinity of 1 year, which shows just the energy is not a big issue anymore you need for production of those. Okay. Take a close look here. What's here is a split up between inverter, the mounting, the cell, the ingot, the laminate. So what's the different parts? So most of it is here, as you saw, the ingot, the production of the silicon, especially if you have the Tucholsky process, as we saw before, for the single crystalline module. Off-grid systems. So this was very common. So when I started to come to Brazil in the early 90s, there was not a lot of grid connection. So most of the systems, they worked where grid was not available. Because photovoltaic was really expensive, and photovoltaic was only applied when there's no grid, for example in space. So price doesn't matter because you don't have any other options. But also here in Amazon, where no grid was present, grid connection cost would be really expensive. You apply photovoltaics. But even then, there was a vision that sometimes you can feed in houses. So this was of Time magazine in the 50s. They thought about making photovoltaic really affordable to the people. So important there to begin time, it was, we would call it photovoltaic 1.0, that it was far away from the grid. Yeah. This was an example here. This was an autonomous farmhouse in Schwarzwald. Before they had diesel generators, and then Fraunhofer Street was closed, and they said, no, you don't have to use diesel generator, you can use photovoltaics, and this was even roof integrated. It's very, this was really a long time ago, and it was really up to date at this time. And so many tourists came to see that because it was very unique. And so the farmer gave up the farm, and she was making coffee for the tourists which come there. And Schwarzwälder talked and came for them because it was more profitable to them to show the PV power plant rather than to feed the cows and so on. This autonomous systems works like this. You have the PV generator. You have here a valve that avoids that somehow energy from the battery could go into the generator. You have the charge controller. You have a 12-volt battery. You should avoid a deep discharge of the battery. So if you have a high load and the battery is already empty, you should switch off the load. Vice versa, if the battery is already full, you should switch off the generator here. If for example, if the voltage is around 40.5 volts. Sorry, we'll sneeze a bit. Okay, you see that the switch off is temperature dependent here, so you have a function of temperature. This and the condition of the battery. So just for example, for Brazil, for example, we just made such systems with some students here. For daily consumption was here 400 watt-hours per day, so it's an elimination in the ventilator, for instance. We have one panel of 125 watts, and usually you should not discharge more than 50% because otherwise the lifetime of conventional batteries will be limited. So you choose here batteries 12 volt, 135 ampere hours. That's just a typical example of what we applied at the time. If you have an inverter, you should consider also the losses by the inverter. So you should have a bigger solar panel and also bigger batteries in order to compensate for the losses caused by the inverter. These are some examples here. So Stecker, Studer for off-grid systems. Here's some charge controllers. Also, this is SMA, this is Stecker, this is American brand, or no, this is a Chinese brand here. Morningstar is American brand which works on that. So layout. How to quickly layout. So this is all I give my students because they ask what's the layout. So this is a really quick layout procedure. So you just calculate the load. So you have all the load and the duration of the load. So you want to watch TV for 3 hours a day, and you want to switch on your light for 2 hours, and you put on your computer for 1 hour. You add this all up, and then you end up at the load here in kilowatt hours per day. And then you, the next step, you determine the battery size. So considering that you would be able to have a complete autonomy, so even if the sun is not shining, you want to have that energy being available. So you consider the maximum depth of discharge of the days battery. Usually you shouldn't go beyond 50%. Then you have the days of autonomy. Usually that's a rule over the thumb. In Germany you should consider that there are 4 bad days in a row when the sun is almost not shining. In the tropics you can consider as a rule over the thumb 2 days are sufficient. So you have here the battery size, the capacity of the battery, so the load times the days of autonomy divided by the depth of discharge. Then you calculate the energy to be generated by PV, so you have to consider the inverter efficiency, the battery efficiency, and the efficiency of the charge controller. And the load, not only the battery, you don't have to fill up the battery entirely because you always usually keep 50% of the charge here. And then you choose the daily irradiance, a typical day of the first month of operation. For example, in Brazil, this would be now, June, July. And then you take an average day, if the system should work the whole day. And then you calculate the area of the PV generator here. And while usually you don't buy a PV generator per square meter, you buy it per watt under standard test conditions. And this is a conversion into the power under standard test conditions. So this is just the area times the irradiance under standard test conditions with 1000 watt per square meter times the conversion efficiency under standard test conditions. Here, this one you find here from this formula. So this is a quick procedure, though in 5 minutes you can lay out system and it works quite well. So for larger system you have a simulation program for that. The market for the autonomous systems is like this. For example, if you have a watch or a torch and a cattle fence, they have usually small batteries. And if you calculate the costs per kilowatt hour, they are really expensive. So such a small battery is not expensive, costs 10 reais or something like this, but the energy content is very far away from 1 kilowatt hour. So you have to buy a lot of battery to get 1 kilowatt hour. At the end you pay about 10,000 euro per kilowatt hour for those kind of battery. So there, photovoltaic is really competitive. You can have it really 1,000 times cheaper by photovoltaics if you would have such a if you have such a system. So also for electrical cattle fence batteries, I still wonder that most of the cattle fence batteries are throwaway batteries, and why are not using so much photovoltaics on that? I don't understand, because it would be much cheaper. Also for the gasoline generators, the small generators you see a lot in everywhere, they are more expensive than photovoltaic. Or the diesel generator, 10 kilowatts. By the way, the orange line, this is orange area, this is for Germany. The yellow part is for Brazil because the irradiance is higher, therefore the prices for photovoltaics are lower, so it's more competitive. Even if you consider a battery and grid, you're still competitive in some parts. So this is for a normal tariff, including photovoltaics plus battery, is still more expensive than that. If you have photovoltaics without battery, you're already much cheaper than the grid. So this is, for example, the cost layout for such a system. So they calculated. So this is for 20 years of lifetimes. This is a really good battery, an expensive battery, which lasts for 10 years. Some bad batteries, sometimes they only last 2 or 3 years, but this is a really good battery. But even you have to change it after 10 years. And for the total calculation of such a system, it's 51% related to the battery costs. For modules, it's 20% only, because they got so cheap now. So you shouldn't really talk about a photovoltaic system. You should use talk about a battery systems with PV support or something like this, because the largest share of costs are here in the battery side. Installation 7%, support structure, charge controller, inverter. So inverter plus charge controller is about the same cost share of the as solar modules. Important points for PV implementation. So first, you should make a project identification, irradiance, land, security. So if it's a big danger of theft, you should think about making a fence or having some people here who observe it, or surveillance cameras. Even in Germany, that's an issue. Grid connection. How far is the next grid connection point away? Are you allowed to feed in there? What's the maximum capacity? This was a bit of a problem in Chile, that they installed a lot of PV systems there, but then they found out that the transmission lines were not good enough, and a lot of projects stalled because there were 2 gigawatts of PV systems in the line, and the transmission systems was only laid out for 1 gigawatt, and so they had to wait a long time. So this you should know in advance. Legislation for grid feeding. So really important. Usually a bank requires that already. So what PPA do you have? Power purchase agreement. If the system fails, you have to pay something extra, or how secure is that legislation? For example, in Spain, they made the legislation and then they found out it gets too costly, and then they stopped the law. So that's really not very helpful. So it stopped all investors to invest in Spain if you do it once. Since that, the Spanish PV market was dead since they did that. So if you have one legislation, you should keep it. So otherwise, this would be really poison for the investors and so on. Financing, I mentioned already the PPA. Maybe in the future becomes more relevant again. Carbon trading. At the moment, the carbon price is very low, but in the future it may rise again. So you say, okay, you are clean energy, and you have a very low carbon dioxide emissions, about 70 grams per kilowatt hour. If you compare it to coal, which is about 10 times higher. Taxes, tax reductions, especially in the United States. So if you have a PV power plant, you can reduce your company taxes and so on. Subsidies are not so relevant anymore because we are really cost competitive now with photovoltaics. Interest rate, that's really important. So that's really a big issue. So even if we have very low module prices now, if you have this high interest rates as in Brazil, most of the projects are not feasible. Beyond 10% of interest rate, it's really hard to make cost because you have long-term investment and so on. And inflation. So this is, for example, if you have a feed-in tariff that sits fixed in a fluctuating currency, you have to consider that. How much is your feed-in tariff worth in 10 years or in 20 years? Equipment. So you should really consider that your components are really suitable for high operating temperature, high sand and salt content of air, UV stability and warranties, because you are all operating outside. Usually this inverter and batteries, they are usually made for operating inside a laboratory or something like this. This material has to really withstand high temperatures. Usually if you take a data sheet of one conventional electronic equipment, it always say operation between 0 degrees plus 40 degrees. That's not enough. You should really be able to operate from Germany, at least from minus 20 to plus 55 degrees. Brazil, maybe even 80 degrees would be suitable to have, if you consider sun outdoor temperature can reach almost 50 degrees, plus the solar irradiance, plus the internal production of heat of the equipment. And you should have also, if you just purchase your thing, you should have a local dealer. It doesn't help you if you have a warranty in China, so you have to deinstall the module, ship them to China, ship them back, and maybe the company doesn't even exist anymore, and so you should have really a local dealer which can deal with that. Best is if you have such good quality, you don't have to have these cases, because this is a really enormous cost nowadays if you have to deinstall the modules, find the fault, and then get the warranty issue. Infrastructure. So you have to consider importation. This is a big issue in Brazil because the import taxes are high, the duration is long, and so on. Sometimes there is a strike, and then your whole project planning is any question. Transportation to the point of so this is sometimes if you have go to a very distant part, maybe an issue. Mounting equipment, tools, accessibility of location of installation. For example, if you install do a net metering and you install on a factory roof, which is not your factory but from someone else, you should really make sure that all your workers can go into this factory and go there and have access to that, which is not always the case. Good installation team, that's really important. So many people are not educated to this photovoltaics, so you should really have an experienced team. Also training of a local supervisor, so you don't have to send in your expensive experts from outside of the country. Maintenance, also a big issue, so you should have something there if there are faults who can quickly act. And it's already paid to do this, otherwise there will be first negotiation, how much will it cost, how much does it take, and so on, and during that time you're always losing money. Problem management, also future development. Sometimes if you have quick developing areas, the energy consumption will increase quickly, and you have a power supply system, you should be able to expand that system. Even there are non-technical issues for PV implementation. So sometimes culture is a very short-term solution, so people are a bit afraid of investing for 20 years. I usually was talking to Brazilian investors, they always want their money back within 2 years. So this is a big question. We know, say you get it only in 4 years back, it's too long for them. Focus on centralized large-scale solutions, especially goes to the politicians. They want to really have a big party and really huge plans, and where they get famous, and a lot of press photos are there. And so photovoltaic does not serve for that. It's silent, it's nice, it doesn't sound as spectacular as nuclear power and so on. It sounds crazy, like a childish, but it really plays a role. This is really important that the nuclear power makes the country more powerful and so on, and solar is somehow weak or whatever, so this is a psychological factor here. Deficits in education, so people don't know how cheap photovoltaic is really now. Been in Nicaragua, and been talking to the energy minister, and he showed me a proposal for a 20 megawatt system which costs, it was a 2 megawatt system which costs $20 million. It's absolutely crazy. It's more than $10 per watt. You can cross one zero weight. It's still expensive. So this is so photovoltaic. You shouldn't pay more than $1 per watt nowadays. This is not really cheap for the whole system, not for the module, which is only half of it. And so therefore, it's very important to educate authorities. Just at the university here, make some courses to educate the authorities. Because usually they are trained, the authorities, 30 years ago, and their photovoltaic does play a role, and so they should know really about the possibilities and the actual costs of photovoltaics. Legislation, so the crazy situation also happened in Brazil, that there was a subsidy for diesel in the Amazon, but not for photovoltaics. So this changed a bit with some programs, but for some time there was even, so you get a subsidy for diesel somewhere else, and photovoltaic would have been competitive, but while there was a diesel subsidy, it wasn't competitive. So this should be avoided. Long-term financing, yes, it's a high interest rate, it's really a problem. If you have high interest rate, this inhibits a lot of projects. And missing marketing and lobbying. So while the established energy companies, they have a long-term lobbying, they have lots of money, they have lots of experience, they have very professional talkers to do lobbies, and the solar community is more diverse, and so they don't have so much access also to the stakeholders and to the politicians and so on. Okay, this was just some general remarks, so you should still be valid. So just to so this was first element. Let me jump back. What happens? Yes, this was about PV 2.0. This is now important that you have here feed-in legislation, so you should be allowed to feed into the grid. So this was the house, I think we've been talking in the lunchtime here. This is in Freiburg, southwest of Germany, very close to the French border, the Swiss border. So they have totally self-sufficient houses here. So they even produce more, they call plus energy houses than they need, so they sell to the neighbors and so on. And during nighttime they have some biogas power plants, and they are totally auto-sufficient here. This is at the Munich airport if you arrive there, so it's also a 2.2 megawatt power plant here. This is in Portugal, Serpa, 11 megawatt power plant. So first people start to, not to talk about any power plants, it's called photovoltaic landscape. So the even landscape architect thinking about how we can arrange it that it looks nicely and so on. So it becomes more into 11 megawatt is not really big anymore. So this is a 67 megawatt power plant in Germany. It was an old Russian airport in eastern Germany. So they cover this area. And here very close to Berlin, so if you want to visit me to Berlin, it's just 1 hour drive. Here it's an 84 megawatt power plant. As I told you, the biggest one are half a gigawatt and even 1 gigawatt is in planning. So this is a 100 megawatt here in China, so this is a panoramic photo. A bit hard to see here, just photovoltaic models are around. Related to that, there's also innovation for you. But when it is not only thinking about photovoltaic cells and so on, there's a lot of industry related to that. For example, here, for example, cleaning robots. So there are some companies work on that, how we can do the maintenance or the management. If you have a 100 megawatt system, you just really think about how you can perform that. The issue was how we can avoid it without using any water, because many countries they don't have water but a lot of dust. Or here in Brazil, São Paulo would be the same issue, how you can clean the module without water and without scratching the surface, because many modern solar modules, they have anti-reflective surface, and it's very sensible to scratching, so they should be avoided. There we already did some research about how to avoid scratches and even get clean. So we come now to the market development, the costs and so on. Quite interesting subject. So this is a logarithmic scale of the cost in relation to the cumulative production. This fits quite well. So if you are producing more, the price is going down. See it here from 80s to 85. So you see here prices have been here at the 20 euro per watt. So a single solar cell with 1 watt costs 20 euro. Then there was in Germany, it's a big initiative here with the German Feed-in Act, the premium tariff, and you see here, within 5 years only, the price dropped significantly from about, how was it here in 2000, for example, about 1 to 3 euros per watt, then 2010 it was in the vicinity of 1 euro per watt. So there was a significant price reduction within quite short time. Still continuing, but not so fast anymore. As a terminal rule, you can say within the last 36 years, experience was if you double the production, the price goes down by 24%. The more you produce, the cheaper it gets. So nowadays we are here in the vicinity here about 20, 30, 40 cents per 30 to 40 cents per watt, without import tax. That's what they do. So this is from the manufacturer. So here you see a small scale system, not the big systems. It's much cheaper, but here for the small scale house, the costs developed quite quickly. So this is here 2006. So costs have been for 1 kilowatt system in the vicinity of 2008 even in the 4,000 euro per kilowatt. Nowadays they are just 1,200 euro per kilowatt. So it's including everything: installation, modules, and inverters for small scale. For large scale, that's much cheaper. You see here the share of modules have been very big at the beginning. Nowadays, the so-called balance of system costs account more than the actual module costs. The module costs here, orange is the BOS costs. These are about 52% of 48, and here it was 70% for the modules and 30% for the BOS.
I have a question.
Yes?
I have a lot of questions. I'm asking and you can reply me?
Yeah, sure.
Okay. I was thinking about two things that you are talking about, that make like a declined automatization that I think it's really nice. But I was thinking how much this costs, and I was thinking about what is the price, like the manual maintenance at like the automatic cleaned. What is the difference in price?
So this applies only for large-scale systems. So, for example, if you have 1 megawatt system, it's about 4,000 modules. That's not feasible. But if you go to 50 megawatts or something like this, this makes completely sense because then it's cheaper than manual cleaning. This depends on the local cost. If you go to India, you get a worker for $2 per day or something like this, and it's manual cleaning. If you go to Sweden or something else, then you pay $50 per hour or something like this. So it makes more sense to get a cleaning machine.
From India to go to
So this depends on local, but most of the larger power plants, they already have these machines. There are a lot of competition now because there are different manufacturers, different qualities, different prices and so on. We tested it at our photovoltaic institute in Berlin, so we just compared some of them, one in Israel and one in Saudi Arabia, and we just checked them. The main issue was the scratching here, so they just want to make sure that no scratching occurs due to the mechanical brushing of the modules and so on. So there must be a publication on that. You can find out if you can send me an email or something like this. I can send you that publication on that.
Okay. Another question is about you say about that you have like already integrate equipment that say when the equipment is damaged, and you say that all of them have this equipment. But this increase the price of the solar panel that they don't have this equipment to say when your photovoltaic cell is damaged.
I know. Usually the solar module. This was planned to have smart modules which have that opportunity that they say I'm damaged or not. Usually this kind of diagnostics is in the inverter side. So this inverter, if you have a really centralized inverter, it can't know which module is really in danger. So if you have 1 megawatt, it might be, he can only say that the total power output is reduced and you have the choice of 4,000 modules, which can be wrong. If you have a string inverter, and one string is 20 modules, so you have to check the 20 modules. If there's one string inverter saying, okay, our power output is reduced, there must be something wrong with one of the 20 modules. If you have a module inverter, it can really say that this module he's working on has a reduced power output. So this depends on the amount of money you spend on this diagnostics on what you have. You can also do surveillance. So we have a drone and with an infrared camera, and you see where there's a local heating up of the modules. As we saw before, when the module is working at high efficiency, the temperature is cool. When there's a problem with bypass diodes or shadowing or something else, then it's heating up, and you can identify it via an infrared drone. This is also sometimes done to get to find out some problems.
I don't know if it's some research about, for example, when one cell is damaged, like isolate this cell or don't overcharge another cell close by. I don't know if you see something like this, or...
Then it's a hotspot issue, for example, is when there's a shell settled, and then you have the high voltage, not only the module. If you have more cells interconnected, more modules interconnected in series, then there could be even up to 1,000 volts at a single cell, and it can really burn that cell if you don't have bypass diodes and so on. Then it's usually it burns, but then it makes a short circuit, and then it's a permanent bypass diode. So this is possible, but it's usually doesn't damage neighboring cells. I'm not aware that we have some problem with neighboring cells. So the cell is permanently damaged. Yes, it looks ugly. Also, it looks burnt. So sometimes the glass may break. Then it's a serious issue. Then it can damage maybe in the long term. Neighboring cells also, because then vapor and water can come in, and then the module is really well.
Do you know any program to make this simulation for size your system? That I know some programs, but all of them it's not open. This is not open, you have to pay for
Yeah, usually the professional programs, they cost PV for example.
Yeah, but do you know some
this is by my colleague for the Kvarschnik, he made green tea, he made some programs which are for free. Green tea or something like this. I can give you the link for it. So this is from the university, also Berlin University of Polytechnics University, Fachhochschule, they have some program. I can send you some. Okay, but I have to continue the talk otherwise. Or is there a very important question still? Another question, or are you? No. Okay, no, because give me a sign, you have only 10 minutes, otherwise you miss the rest of the talk. So. Okay, prices. So this was the prices for small scale systems. Oh, it doesn't work anymore. What's happened? Oh, it's on. So this was a price development during the years. Interestingly, this was a prediction from the year 2000. So in the year 2000, this was for the Iranians equivalent to Germany, and power output, so this is equivalent to full load hours, because the conventional power plant operators always calculated 900 kilowatt hours per square meter per year. So a little bit underestimated, but okay. At this time, production costs of photovoltaic plants was about 60 cents per kilowatt hour. Same Brazil here, it is about the Iranians of Rio de Janeiro, 1,800 kilowatt hours or 1,800 kilowatt hours per square meter and this is about 30 cents per kilowatt hour. And then the prediction was for 2020, so we should arrive here in Germany for 22 cents per kilowatt hour, and in Brazil it should be here the vicinity of 10 cents per kilowatt hour. So this was a prediction in the year 2000. What actually happened is that in the year 2010 it got actually much cheaper than expected. So because through the big success of the German program, a lot of investment in production equipment has been done, and then it was already in 2015 when we reached in Germany the 10-cent barrier, and in Brazil it is possible to do at 6 cents per kilowatt hour, and nowadays we have even 6 cents in Germany. So this 2018, so the last tenders have been there. These are tenders all over the world. So you see the tenders here from 2012 to 2016 or to end of 2016. So this is wind power tender. So here's in Brazil. So this is not in euro per kilowatt hour. This is US dollar per megawatt hour. So if you put equal US dollar and euro, you see this is equivalent to about 5.5 cents per kilowatt hour for wind here. So the last tenders for wind, so here the vicinity of this 6 cents per kilowatt hour. And photovoltaic has always been higher than that. Only in year 2016, photovoltaic achieved to be cheaper than wind. So there in the Arabic states, or here Mexico and here Dubai, Abu Dhabi, they achieved prices now here in the vicinity of 3 cents per kilowatt hour of photovoltaic energy. And this was quite interesting news, because it is cheaper than wind, this is cheaper than everything. So here the translation, here 1 euro is equivalent to $1.17. So this translated to euro is about 0.026 euros per kilowatt hour. In 2017 they have even below 2 cents per kilowatt hour. It's not built yet, but these are built now. So this now more of a global perspective. What do renewables have share on global electricity? You see the constant increase here, 2007. It has been, there are two colors here. This is for global capacity, and this is the capacity change, and this is the generation of it. So this is the actual generation because you need more, you have more full load hours at conventional power plants rather than photovoltaics. So here you see the renewable generation here from 5%, now we have 12%. So it doubled, more than doubled within 1 decade, globally, not only in Germany or some selected countries. So we have now 12% of renewable share of renewables. And for capacity-wise, it's much more. If you see the new power plants being developed, so new capacities added in 2017. You have here solar, total was almost 100 gigawatt, 98 gigawatt. Wind was 52 gigawatt. Coal was only 35 gigawatt. Gas, nuclear, almost only a very few have been built. It was on the rise. It's just so people are saying, yeah, yes, China is building a lot of nuclear power plants. It wasn't true. You see here, these are the actual numbers. Just some fake news here. Large hydro have been built a lot more than double as the nuclear, so 90 gigawatt, and others 7 gigawatt. So you see that by far the renewable energy are leading here. What's been the new installations in all worldwide in all types of generations, all kinds of generations. If you go more a bit into details of photovoltaics, here this is the total PV capacity installed globally, not per year, but in total. Nowadays we have now a total capacity of 404 gigawatts installed globally for photovoltaics. Here in this time, the blue one is Europe, basically Germany, then Italy and Spain were doing that. Now they're losing a bit the position here. There is just much more happening in China here. China is really doing almost half the world market here. But also here in Asia, the rest of Asia without China, so that means India, Arabic states, Africa, and so on. And also America is also including North and South America, also happening a lot since 2012. Per year, so this is the end per year. So last year, as if we know, 98 or 99 gigawatt have been installed. And most of them in China here, more than half of it in China, a lot of it in the United States, and also in India and other Asian states. Europe is still a bit, at the moment, not so much happening. Okay, so let's be clear. This is a world market shares. So as I told you, 32 are in China, but also Japan is quite strong. India, USA, Germany, so this is the different shares. Fortunately, Brazil is not here because it's under 1%, and it's not on this map, so this is just down to 1%. And they've included here, the rest of the world is 14%, so lots of countries have in this facility. So here you see the top world markets and also the prospects. So this the prospect for Brazil is not so bad because here it's on the top 20 still. So here you have China, so they expect that new installation for a high scenario will be additionally 283 gigawatt and so on. India will be also expected 100 gigawatt. USA, Germany, there will be also some additions here. Australia to another 26 gigawatt and so on. And here for Brazil, expect to be, we can read it here, to be 9.3 gigawatts. So this is almost 10 times more than has been installed now. I think one in the vicinity of 1 gigawatt has been installed. Yes, please.
So, you've been showing us these charts, and I've been wondering, why do you think Europe stopped investing so much on PV?
No, it's not leading anymore. It's just China is much bigger than Europe, so it's just these issues in Europe I come a bit later because there's sometimes saturation problems. As I told you, that sometimes some days we have most of the energy comes from photovoltaic, so people have to digest that amount of power, so they have to store it or to give it to other countries and so on. And I come to this a bit later in the third part of the things where we talk about policies and actual situation and actual trends at the moment. So I'll come to this a bit later. Yeah.
Professor, I don't know if you have more time later, so I have to ask you, in your opinion, which is the next challenge for photovoltaic energy? It's get scale up the production to reduce to decrease the price. Is develop new photovoltaics with better efficiency. What do you think that?
Well, because the price is already very low. It's not, if you think about, you have 2 cents per kilowatt hour, and you are paying now in Brazil about 20 cents per kilowatt hour, 1 real per kilowatt hour. So it's not the photovoltaic which makes electricity expensive. It's 90% in between 2 cents and 20 cents. Where are these other 18 cents? Where are they going to? So they should think about more about that. That's distribution, that's taxes, that's transmission, and so on. So even if you reduce by from 2 cents to 1 cent, what would make a difference? It would be 1 cent of difference. So even if you spend all your efforts, spend a lot of money in the universities to get more efficient solar cell, you would only reduce the price by 1 cent, and there's still 19 cents are still left over. So it is, and you come to this in the third part of the session. So it's a bit unusual if you talk about solar cells, not to invest more in solar cell technology, but it's actually true. If you see the value chain of that, it's not the solar cell that makes the solar electricity expensive.